Welcome to Physics 150 podcast of Chapter 14. At the end of this podcast, you should have a better understanding of internal energy, heat capacity, specific heat, and the specific heat of an ideal gas. So let's get started. First of all, how do we select a system? Well, we've talked in the past about choosing a system to analyze and predict some variables of the system. We have chosen blocks, springs, balls, projectiles, cars, boats, people, etc. When we choose these systems because we were concerned with how these systems acted as a whole. When we do this, we have no idea what is happening inside the system. Now we will be talking about an idea that will allow us to predict some interactions inside the system. So this idea is internal energy. All larger systems must be made up of smaller objects. An example would be a volume of gas. The gas is made up of many molecules. Each of these molecules have an amount of kinetic energy. We can model the average kinetic energy by using, not but using, this expression for the average kinetic energy of a molecule of gas, where T is the temperature of the gas and K is the Boltzmann constant. The energy of the system that is contained in the motion, in its motion, the kinetic energy and the interactions, its potential energy of an internal object. Basically, the internal energy of a system is the energy associated with the individual molecules or constituents' kinetic energy and their interactions with the other molecules inside the system. We are not concerned with the macroscopic kinetic energy or potential energies. And we do not include the macroscopic kinetic energies or potential energies of the larger system as a whole. One of the ways we can measure the internal energy of an object is through its temperature, and this allows us to get a value for the average kinetic energy of the constituents inside. We're going to talk about heat. Heat is kind of like work. Work is the transfer of energy from one object to another by using a force. Heat is the transfer of energy from one object to another by using a difference in temperature. The energy is transferred from an object with higher temperature to an object with lower temperature. When the temperatures of the two objects are equal, the two objects are in equilibrium. So we're going to need the units to describe this. The unit of a joule is kind of small when we deal with energy transfer through heat. So we're going to use a new unit called a calorie, and that's spelled with a small c. It's sometimes called a heat calorie. And 1 heat calorie is equivalent to 4.186 joules. 1 large calorie, or capital C calorie, is 1,000 calories, little calories, and that's equivalent to a dietary calorie. So if you look on the back of a food item and it says it's 200 calories, that's 200 dietary calories, or 200,000 heat calories. So if you increase the internal energy of the object, you can actually change the shape of it, of the object itself. Space between the microscopic items making up the object can actually change. The space can get larger, and this is what we call thermal expansion. Now, the way every system has the ability to store internal energy, and the way we calibrate an individual system is the thing called heat capacity. Capital C, heat capacity, is the relate of Q, the amount of heat transferred, divided by its change in temperature. I should say Q is the amount of energy transferred through the difference in temperature. And then if we divide that big C by the mass of the material that is transferring this energy, we get specific heat. And if we rewrite this equation, we can get a value for the amount of heat energy transferred through heat. We have mc delta T. You might have seen this in some of your chemistry classes. Now, if Q is greater than 0, energy is transferred into the system. If Q is less than 0, energy is transferred out of the system. So here's an example. How much heat is required to raise the body temperature of a 50 kilogram woman from 37 degrees Celsius to 38.4? I calculate my change in temperature by taking the final temperature by the initial temperature, and if we do that, I get 1.4 degrees Celsius. I need to figure out the amount of heat energy transferred, and the amount of energy transferred using heat, and there I use my expression for Q. I plug in the mass of the woman. I plug in the change in temperature of the woman. The one thing I don't have is the specific heat of the woman, but that leaves us with the question, what is the specific heat of a woman? And you think about it, what is the major portion of the human body? Wait for it. And that is water. So we're going to estimate the specific heat of this woman as being the specific heat of water. So if I plug that in there, I get a energy transferred by heat to be 293 kilojoules. Now you'll notice that my temperature, change in temperature is in Celsius, but if you look at my specific heat, its change in temperature is Kelvin, but if you take the difference in Celsius and the difference in Kelvin, the change is the same amount. So 1 degree change in Kelvin is equivalent to 1 degree change in Celsius. It's just that the Celsius scale has a different value for 0 than Kelvin. Alright, here's another example. You have an aluminum tea kettle and 200 grams of water at 15 degrees Celsius. How much energy needs to be transferred through heat to raise the temperature of the water in kettle to 100 degrees Celsius? So what you need to learn here when we're using these concepts is the fact that the system needs to be in equilibrium for this to be true. So the tea kettle and water should be at the same temperature at the beginning, and they should be at the same temperature at the end. So basically the total Q, or heat energy transferred, would be equivalent to the heat energy transferred into the kettle and the heat energy transferred into the water. I can calculate that with our expression. The change in temperatures are equivalent. It's 85 degrees Celsius. I need to plug in the specific heats for aluminum, the mass for the aluminum, specific heat for water, and the mass for water. And I come out with 7.42 times 10 to the 2 kilojoules of energy transfer into the water in the kettle. Alright, here's another problem. We have a blacksmith heats a mass of iron to 498 degrees Celsius in his forge. After shaping it into a decorative design, he places it in a bucket of water to cool. If the available water is at 20 degrees Celsius, what is the minimum amount of water? Must be in the bucket to cool the iron to 32 degrees Celsius. and they state that the water in the bucket should remain in the liquid phase. That'll be more important on Monday than right now. But what we have is the heat energy that is going to be transferred from the iron into the water. And if we calculate that, you'll notice that our final temperature is smaller than our initial temperature. That gives us a negative value for Q of iron. We have to calculate that energy from the iron gets transferred to the water, but it'll be plus Q because the temperature of the water is going to rise up. And so we know that our change in temperature of water is going to be 3 degrees. We know the specific heat of water. So if I rearrange the equation to solve for the mass of water, I find out that we need to have 6.23 kilograms of water to cool the piece of iron. Alright, so how do we calculate specific heats? One of the ways you can calculate specific heat for an ideal gas is basically we use the average translational kinetic energy of an ideal gas is this. So every molecule has this average energy. And we're going to assume gas has this. So what's the total kinetic energy in a gas? Well, it's the number of molecules times its average kinetic energy. We use this. We can convert it into the number of moles. We have two expressions of this, where big N is the number of molecules and little n is the number of moles of gas. Then what we're going to say is if we have a change in kinetic energy, that can be equivalent to the energy transferred by heat, and then we can calculate the specific heat. And so we take this expression, we divide it so we can calculate the specific heat for a volume of gas. I should say, we can calculate the heat capacity for a volume given a gas to be this. And this only works for monatomic ideal gases, so 1 atom per molecule. I believe this is the end of the podcast, so I hope you understand more of the things. I hope you understand the idea of potential energy better, how heat is the transfer of energy by change in temperature, and how to use that to calculate particular amounts of energy change or internal energy change of objects. But in this case, these are all equivalent to a certain amount of energy, because you can have energy stored in kinetic energy, potential energy, or the internal energy of an object now. This should be our last podcast. I'll be back on Monday to answer questions. Have fun, and see you on Monday.